and CH812 post mid-semester session. Okay. So the recording is on. So yeah. So let us start. Not this one. Okay. So I'll just show you this. Day before yesterday, we were doing something like this. You remember? I told you that if you take the ladder operators, like raising and lowering, they're called ladder operators, expressed in terms of Lx and Ly, x component and y components of angular momentum operator, orbital angular momentum operator. Then when it operates on a wave function, it either raises or lowers the wave function. But then it comes with a coefficient. The coefficient is given by this. I did not show you how to derive this coefficient. This is going to be one problem in your assignment, which I'm going to send this Sunday or Monday. Okay, this first set of assignments. Then I said, okay, you can make an analogy with this. Just map this onto spin. You have like Sx, Sy, like Lx, Ly, Lz, and they have the same commutation relations. S square operates on Sm, gives you h cross s square, small s times small s plus 1, then the wave function back. This is a Bryan-Kate notation shown here. This is a Kate vector. I can use a simple notation like alpha, beta, because when I did with electrons, you have two spins. Yes?
Sir, are you sharing the screen?
Oh, I did not share. Okay. Yes. Yeah, so now you should be able to see. So
yes, sir,
yeah,
it's
but
visible.
anyway, I'm going to start now. I'm just spending few minutes. Okay, then I'll start and yeah. So this is like Sx, Sy. So I told you that these are coefficients. So similarly, S plus and S minus will have the similar coefficient expressed in terms of small s and ms. Okay. So
Sir?
I did not derive this. I said this will be an assignment problem. Yes, tell me.
Sir, I have one doubt. In the like up spin alpha, we write half and half in the cat notation.
Yes.
So why we are using two half? Because alpha is plus half.
Not L for S. I'm talking about spin now. I
Yes.
put like S half half. Alpha means half half. Beta means half minus half.
So alpha is up spin. So we can only write. We can also write plus half only.
No. AL is for angular momentum, orbital angular momentum. No. We have for AL you have this wave function, this spherical harmonics, isn't it?
No,
You
sir.
don't have. Yes.
I'm telling like we write two plus half here in the cat notation.
Yes. Not for
So
L. This is for spinners. These are called spinners, isn't it? This chi plus and chi minus. This is like alpha beta. Alpha is like half half. Beta is like half minus half. This is for spin. Nothing to do with orbital angular momentum. This is for the spin. This is for S square and sz. These two operators, S square and sz. You have alpha and beta. For electron, spin half is plus up. Spin up is plus up. Spin down is minus up.
So, sir,
And
why we are writing 2 plus half?
yeah, because this is the value of S and this value of ms. S is always half for electron, isn't it?
Okay, okay.
Yes, that's right. And you have 2s plus 1, which means half into 2 plus 1, which means two
Yes, sir.
state. One is plus half, another one is minus half. That's all. Very simple thing. So another way of writing this is using column vector. Chi plus spin up, chi minus spin down. But again, I am telling you, there is nothing called spin up, spin down in that sense. This is quite useful because spin is not like a classical object here. Chi plus, chi minus. Okay. And then I said, okay, then a square operating on chi plus, which is basically a square operating on alpha, should give me this times the chi plus back, which is like 3 by 4 h cross square chi plus. So then I said, okay, let us represent this a square with a matrix, 2 cross 2 matrix. C, D, E, F, these are the matrix elements. And chi plus and chi minus, in the previous slide I showed you, these are like column vector or column matrices 1, 0, 0, 1. Okay. So then if I operate a square on chi plus, I could find out the coefficient, the matrix element C and E. Similarly, when a square operates on chi minus, I can find D and F. So you can see this is like a diagonal matrix. So this is the expression for a square, which is 1, 0, 0, 1. Of course, you have this factor 3 by 4 h cross square. So we'll start from here today. Okay. So let us start. Someone, okay, let us start. Can you see the screen?
Yes, sir.
You can see, no? Okay. So let us start this. Okay. So what I had, let me tell you again, when S square operates on chi plus, what should I get? Tell me for electrons. Somebody has to tell me because I want to see that they are following.
3 by 4 h square.
Yes. Then the chi plus back. Similarly, when S square operating on chi minus, that gives you
The same eigenvalue.
yes, very good. And I use this relation and I showed that in the last class that sorry, a square is given by this matrix. Okay, let me have to write the prefactor. A square is given by this 3 by 4 h cross s square, a diagonal matrix 1, 0, 0, 1. Okay, I think we stopped there, isn't it?
Yes, sir.
Yeah.
So we stopped there, and so let us do it for this operator S plus. If I operate S plus on chi plus, what should I get? Any idea?
H cross.
Zero.
No. S plus on chi plus, it will be, somebody says, it will be 0. But if I operate S plus on chi minus, what should I get?
Chi plus.
But I'll have a coefficient here, no?
H cross.
Yes.
And how do you calculate the coefficient?
Root SS plus 1 minus.
Normalization.
Yeah, I gave you that expression, no? Somewhere it is there. This is the one, no? Okay? This is the one. So let us do it. So if you go back and check, you'll see that if I operate S plus minus on chi whatever, chi minus plus, it will be something like and this will be like this, isn't it? It should be like this. It should be like this. If I operate this on this, it should be like this. So what is the value is for this coefficient for electron? You know what is the value of S?
Half.
Because we are chemists, so we're happy with electron. You don't go beyond electron. So if I put this here, I'm going to get this coefficient is going to be how much? It is H cross. Let us do it. So I am doing it for chi minus. Chi minus means half, This is minus half, no? Minus half, minus 1, I think. What it is going to be? I think you can calculate. It's going to be h cross. Am I doing anything wrong? Maybe it should be h cross. What is the formula?
I think, sir, in the bracket it should be -1, minus half plus 1.
Yeah. No. Now, S is 1. I'm just looking at the formula. Yes. Yes. So it is ms plus minus 1. Yes. Yes. Yeah. Minus minus. Yeah. So I think, yeah. Yeah, this is minus. And this is going to be. What will be the answer? Can anyone tell me this is? Am I doing anything wrong? Because it has to be h cross, no? 3 by
Sir,
4.
Sir, in the bracket.
it's plus 1 after minus half.
Yeah, this one.
Yes, sir.
So if it is like this, then for example, if I calculate, I'm just looking at this s plus operating on chi minus, that will give me chi plus. And the coefficient is going to be, you see it is in h cross 3 by 4 plus, this is 1 by 4. So this is going to be h cross. So that's why it is h cross, no? This is fine with all of you? Should be fine. So now I make use of this fact. Okay, I I put S plus with some, what do you want to call it? Say E1, E2, E3, E4. So if I operate S plus on chi plus, I get 0, which means what? Chi plus is, remember, 1, 0. This arrow is for matrix multiplication. What should I get? Can anyone tell me? It is E1 plus 0 and
E3.
E3 plus 0. This is what you should get, isn't it, when you do this? But this is equal to what? This is equal to 0, 0. This implies what? E1 is 0, E3 is 0. And now I do the other thing. So if I operate now S plus on chi minus, I should get H cross chi plus, which basically means E1, E2, E3, E4. Chi minus is 0, 1. I should get H cross 1, 0. Okay, so this implies, again, it is E2, E4. If I multiply these two, that is equal to H cross 0. That implies what? What is the value of E2?
H cross.
E4 is 0. This implies what? What is the matrix representation of S plus? So the S plus is now going to be H cross. I can take common. What are the elements? E1 is 0, E2 is 1, because H cross I have taken out. This is 0, this is 0. This fine? I hope everybody can follow. Is this fine? S plus.
Yes, sir.
So how can you calculate S minus? How can you calculate S minus? I am not going to do it. You can do it yourself. S minus, if you do the same way, the matrix representation of S minus is, this is S plus, and S minus is just check yourself. Okay, this is the and S minus operating on chi. Can anyone tell me? Find this coefficient. You have the formula, no?
Yes, sir. H cross
Huh?
0 0 0.
So this will give you S minus. Now remember what is Sx? Sx is, can you express Sx in terms of S plus and S minus? I think it should be. What is the answer?
S plus plus S minus by 2.
Yes, yes. This is your Sx. Anish, your, I think microphone is not working maybe properly. Sx is this. What about Sy? Let me write with 2 i's I, yes. Okay, is this clear? So now let us find the matrix representation of Sx. Sx is going to be what? Half. S plus is this. H cross 0 1 0 0. Someone, the background noise, I think. Can you please, yeah, mute yourself. Thank you. Half H cross 0 0 1 0. You know how to add two matrices, no? All of you? All of you know? 0 plus 0 is 0. 1 plus 0 is 1. 0 plus 1 is 1. So what is this? This is the Sx. What about Sy? It is very easy to do. 1 by twice I. You have H cross, of course, because of this. 0 1 0 0 minus what is the answer? H cross by twice I can take common, and later I'll do something. 0 minus 0 is 0, 1 minus 0 is 1, 0 minus 1 is minus 1, 0 minus 0 is 0, and then I multiply I in the numerator and the denominator. So it will be I H cross by minus 2, 0 1 minus 1 0, and this will be, if I take this I inside and minus 1 inside, it is going to be H cross by 2 0 I 1 0. This is your, sorry, 0 minus I 1 0. This is going to be Sy. Is this clear to all of you? This is Sy.
The second row, first column is I.
Second row, this one is I.
Yeah, so that's 0 1 minus
Yeah,
1.
you're right. I. Okay, because this one goes there, this one goes there.
No,
Okay.
sir, not that one.
Then
That is minus I.
that is minus I. Yes.
That is minus I. The other element is I. Other non-zero element.
Yeah, because I take this. This is what you're saying, no?
Yes.
Yeah. I take all the i's inside. Actually, I multiply with minus I all the elements. So this is how Sy is. So you have Sx, you have Sy. Okay, is this clear to all of you? It is Sx, Sy. So in general, one can write any this S operator is I can call it like h cross by 2. I can take something like sigma, and sigma has 3 components. So sigma x. Now sigma x is, can anyone tell me what is sigma x? It is the h cross by 2 times sx, isn't it? Sorry, h cross by 2 into that whole thing is sx. It's only the matrix. You remember what is that? What is that?
0, 1, 1, 0.
0, 1. It should be somewhere there. I don't know where. Yeah, this is the one. Where is that? Yeah, this is the one. What about sigma y? 0, I minus I, 0. What about sigma z? Now sigma z, one should be able to tell me it is going to be a diagonal one, no? Because the z is actually 1 minus 1, 0, 0. How do you get sigma z? How do you get sigma z? You can do it yourself.
You can use the commutator relations.
Yes, yes. You can use many things. You can actually say that, okay, when you know that the hint is like that, because if you operate sz on chi plus, what should I get? What should I get?
H cross by 2 chi plus.
And sz, when I operate on chi minus, what should I get? This is how it is, isn't it? So use this relation, and you know chi plus chi minus. So if I say your sz is, what you want to call it, f1, f2, f3, f4, operating on 1, 0, that gives you h cross by 2, 1, 0. Let me do it here. So this implies what? This implies f1 into 0, f2 into 0, so 0 is h cross by 2 into 0. Similarly, I can do this thing, no? Because I have the same thing operating on 0, 1 gives you minus h cross by 2. So this will give you what? This is the semicolon. Huh? This will give you the first. So if I f1 into 0 is 0, so 0. So it is 0 into f4. That is 0 minus h cross by 2. So this implies what? Your sz is, I can put the h cross by 2 inside. This is exactly what I put here, isn't it? I just take the h cross by 2 common, because your sz is like sx. Also sx is nothing but this is. So I have now 3 matrices, and they are very famous. You know the name? Anyone? Anyone knows the name? These are called Pauli Spin matrices. How many of you knew about it, Pauli Spin matrices? Someone is saying something. Yeah, any question you ask. Anyone has a question I can ask? Am I audible? Any problem with?
Yes, sir, you are audible.
Yeah. So how many of you knew about it, the spin matrices, Pauli spin matrices? Okay, these are semicolon, okay? My handwriting is a semicolon, huh? Sigma x, sigma y, sigma z. Anish, you would know, because you have taken some physics courses.
Yes, sir.
This is very useful because later, or I don't know whether some of you might have taken or will be taking this 442 spectroscopy course. Anish, you have taken or you will take it?
We'll be doing it next sem.
Yes, so that there it will be quite useful. I'm not going to elaborate on this because when people talk about NMR, nuclear magnetic resonance, you go inside the nucleus and you talk about spins of protons. And proton also has S equal to half, isn't it? It is like electron in that sense. So you'll have the same algebra and same spin matrices per proton. Are you following, all of you? How many of you have taken a course on NMR spectroscopy, not the organic chemistry part, the physical chemistry of NMR? You can unmute and tell. Anyone, BAS, MSc, PhD, anyone? Are you following? I have no idea what is
I
going
think we'll
on.
be doing that part for the first time next semester.
Yeah, but what about MSc students? Please respond.
Sir, our courses are compulsory, not elective. So maybe in the
No, not that. During your MSc, are you a PhD student?
no, sir, I missed it.
MSc, yes. So you'll have 442 later. So 442 is the spectroscopy course. So did you have, how many of you had exposure to NMR spectroscopy? Nuclear magnetic resonance. How many of you? This is strange. No one is responding. Are you following?
Yes, sir, we are here.
Ayan, so you are an MSc student?
Yes, sir.
So you had some bit of NMR in your BSc, little bit?
Yes, sir, little bit.
Yeah, so when you get to go through a rigorous course on spectroscopy, I am sure NMR will be discussed, and there this spin matrix will be very useful. You'll see the use of Pauli spin matrices. But anyway, I have shown you how to represent these operators using matrices. You know that another name of quantum mechanics, another version of quantum mechanics is called matrix algebra. So this is essentially what we are doing.
Yes, sir, heard about it.
We are representing operators using matrices. We have sigma x, sigma y, sigma z, s square. All these things are expressed in terms of matrices. Again, the wave functions like spinors, they are expressed in terms of column vectors or column matrices. Okay. So we'll now move to something which I think everybody knows. We'll start doing this. This is called helium atom. How many of you have heard about helium atom in quantum mechanics, in the context of quantum mechanics? I hope you have. Ayan? Because nobody is responding.
No, sir, we heard only about hydrogen atom. Helium atom we didn't get.
Okay. Not even in your BSc?
No, sir, not
Yes,
in BS.
yes, sir. We
Someone
have
said
heard.
yes, sir. Who is this?
Sarang Suman.
Yeah, so what is special? You have 2 electrons. What is your
Yes,
name?
sir. Sarang Suman.
What is your name?
Sarang Suman.
So you are MSc student?
Yes, sir.
MSc student? Okay.
Yes, sir.
You have 2 electrons. We'll talk about it more later, but let us consider 2 electron spin. But before that, let me do hydrogen atom for few more minutes. What is the hydrogen atom wave function? It is given by psi. In the ground state, psi. What is that called? 1, 0, 0. What is the name? What is this orbital? Psi 1, 0, 0. Everybody should know. What is psi 1, 0, 0? N value is 1. Psi 1s, yes. But then I said that you have spin. So if you have spin, then the total wave function is given by psi 1s, which is a function of r, theta, and phi. and then some kind of alpha or beta spin, which is a function of some spin coordinate omega, and the whole thing is called spin orbital. Okay. But obviously alpha means, if you want to do it, is like up spin, and you can similarly have a situation where it is down spin. In that case, the ground state of hydrogen atom would be something like this is down. Up spin, what is the ms value? Half. Down spin, what is the ms value? Minus half. Okay. What is the s value? Half for hydrogen atom. Electron, one electron system. This is okay. One electron you have. So this electron is in 1s orbital. It could be up or it could be down. So two possibilities. Now think of helium atom. How many electrons? 2 electrons. And how are you now then going to write the wave function for helium atom? Any suggestion?
So 4 possible representation can be of helium atom.
Okay, let us see. Let us see. So the configuration is, 1s2. That you know. Huh? Everybody knows. So one possibility is that, okay, I'm using phi, it is fine. Phi 1s 1. 1 for electron. So 1 means R1, theta 1, phi 1. So coordinate for electron 1. 2 means R2, theta 2, phi 2. Okay. But this phi and this phi are different. This is angle, this is wave function. This is fine. Okay. So psi 1s 1, sorry, phi 1s 1, phi 1s 2. This is the spin, this is the orbital part, isn't it? This is fine. And what is the spin part? One up, other one is down. One up, other one is down. Okay, let us do it. So in general, one possibility is phi 1 is 1, alpha 1, phi 1 is 2, beta 2. This is one possibility. What is this? This would look something like this in 1s. Anyway, this is just for your understanding, but not for your deep understanding, just it is useful. What could be the other way? I can think of a situation that, okay, I say, okay, I tag this electron as electron 1 and electron 2 for the time being to begin with. I can also have a situation that, okay, this like this. Okay, it doesn't matter whether you write 1s and alpha, 1s, then alpha, beta. Okay, these two are possibilities. But which one should I take? First electron is up, second electron is down, or the first electron is down, second electron is up. Which one should I take? Can anyone suggest?
Both of them.
So both are equally probable, no? Both are equally probable. So I take a linear combination of these two. Some linear combination. One linear combination is symmetric. I call psi which is some constant is there. I don't want, okay, some constant, say some n, some constant, say a. And then the symmetric combination is something like phi 1s 1, phi 1s 2, alpha 1, beta 2, plus phi ns 2, phi 1s 1. Does not matter how I write, but What is important here that now the 1 has beta spin. So it should be alpha 2 beta 1. This is one combination. What is the other combination? Antisymmetric. It is going to be something, some constant, say b. Doesn't matter what are these constant. You can find it out later. Okay, up to this. This is fine. Can you see my writing? I hope you can.
Yes, sir, it's visible.
Visible, no? Just a, yeah. Now which one? Both are possible, or I should take something else? One of them. Maybe I'll take one of them. And okay, this is a function of 1, 2. I should write 1 for electron 1, 2 for electron 2 coordinates. But actually, then there is a principle. This is called Pauli principle. How many of you know Pauli principle? How many of you know? If anyone knows, please can you tell me what is that Pauli principle?
Total wave function for fermions should be antisymmetric under exchange.
Yeah. So the total wave function, so including the orbital and the spin part, for actually fermions, so I am writing it for electrons. In general, it's for fermions. Is antisymmetric with respect to exchange of electrons. What does it mean by exchange of electrons? It basically means if I do this psi 2 1, I just exchange. In this case, you have 2 electrons, so I exchange 1 and 2. I just change their coordinates. The coordinates of 1 now becomes coordinates of 2, and the vice versa. If I exchange these 2 electrons, then I get a new wave function, and that wave function has to be what? Minus of psi 1 2. Is this clear to all of you? This is very important. It's called Pauli principle. We cannot prove the principle beyond the scope of the course, but you have to take it for granted. Is this clear what I have written here? That psi 2 1 is minus of psi 1 2. If it is the case, then what does it mean? It means the psi 2 1 has to be what? Which one? It has to be, if I go back to the previous slide, could it be this or could it be this? This one cannot be, because if I change 1 and 2, I am not going to get minus of psi 1 2, isn't it? But in this case, if I change 1 and 2, if I put 2 2 2 1 1 2 1 sorry 2 1 2 1 here 1 2 1 2, then I'll see that I'll get the same wave function with a minus sign, isn't it? So only with the antisymmetric wave function it is possible. So psi has to be, total wave function has to be antisymmetric. So I cannot take the symmetric one. How many of you have understood this?
Sir,
Sorry, this is
sir,
minus.
it means that
Minus, so basically that is equal to your psi 1 2. Yes, tell me.
sir,
Tell me.
the wave function that you have written for symmetric, then it's not possible.
Yeah, this is not acceptable for electron. So I can write not Because Pauli principle. This is so. Can you tell me a easier way to write? Let me write down the wave function again, and I'll see. Now, wave function was something like that. Some constant, I'm calling it B. What is that? Phi 1 is 1, phi 1 is 2, alpha 1, beta 2 minus phi 1 is 2, phi 1 is 1, alpha 2, beta 1. Is there a better way to write this? You know, from your class 12 math, I can write this using a determinant. Do you remember determinant? So this is going to be B. I'm not writing, I'll write later. So this is a determinant. How do I write? It is going to be phi. Can anyone tell me? What is the diagonal term? It will be phi 1s 2 beta 2. What will be this term? The convention is the rows belong to the electrons. It will be for electron 1. So you'll have phi s 1 beta 1. This is phi s 2 alpha 2. So the row belongs to electron 1. This is for electron 2. But what I have done while taking the linear combination, I said that I did not say, but I should have said that electrons are indistinguishable. They're indistinguishable particles. So you cannot take only this or only that. You have to take a linear combination of that because of that. So electrons are indistinguishable. Okay. So is it okay to all of you? What I've written here? What I've written here, is it okay to all of you? And this determinant is called, there's a name
Yes,
to
sir.
this. It's called Slater determinant. How many of you knew about it? And now next question would be how to find the value of B. How can you find the value of B? Can anyone tell me? So let us try to find the value of B. Now these wave functions are orthogonal, which basically
So,
means, yes.
so can you please tell something more about that indistinguishability?
It is indistinguishable because two electrons, I cannot tag them 1 and 2. If I tag them, if I exchange them, I should not be able to see distinguish between the situation before exchange and after exchange. So after exchange, so I cannot say if I exchange 1 and 2, I should not be able to distinguish. So I cannot take only this or only this. I have to take a linear combination of these two, because in both the cases, even if you take plus or minus, this is true, no? Square of the function does not change. So both are acceptable before introducing the Pauli principle. So for subatomic particles, if I exchange two particles, I should not, since they are indistinguishable, I should not be able to distinguish the state before and after exchange. So that's why I cannot take only this or I cannot take only that. I have to take a linear combination of this. So what I meant, this and this, they are indistinguishable. So if I take only this or only this, that is not the thing I should do. I should take a linear combination of that. So both are equally probable. I can have a situation, so first one is up, second one is down. Also have a situation that the second one is down, up, and the first one is down. So if you take a linear combination of that, these two, either plus or minus, then that is the way to go. But then we introduce Pauli's principle, and we say that, okay, only the minus combination is possible for electrons. Okay. This is true for any subatomic particle. If they're indistinguishable, I cannot take only one configuration. Like first one is up, second one is down. How do you know the first one is up, second one is down? It's all equally possible. The second one is down, first one is up, because I cannot distinguish between electron 1 and electron 2. So that's why I have to take a linear combination of these two state, either plus or minus. Next step would be Pauli principle, which says for electron only the minus combination is acceptable. So up to this, true for all the subatomic particles, and then choosing this minus combination is for electrons, only for fermions. Okay, let me come back. How do I calculate the value of B, the prefactor? Can anyone suggest?
Normalize.
How do I do that? Normalize. Okay, how do I normalize? I know that if they are real, so basically phi 1 square integrating over whatever d1. What will be the answer? 1. This is also true for, isn't it? But what about this? If I integrate,
It would be 0.
it will be some volume element d tau. It is 0. So I can make use of this. So we have, okay, they are already normalized. What about alpha, beta?
Same thing applies here.
Yeah, so if I write like this, alpha 1 star beta 1 d omega 1, this is going to be what? This is going to be, sorry, I have this is not right what I have written here, so it cannot be 2, 1 and 2. This is fine. Because I only 1 is here, no? This is not there. But for alpha, what should I write? This is what? Can anyone tell me what is this answer?
0.
Alpha 0.
This would be 0, right?
But if I do this, sorry, alpha and alpha, what is going to be? Alpha is
So
alpha is
1.
1. Putting star, but okay, yeah, 1. Similarly for beta. So basically that, then if you want to normalize it, what will the factor will come here? Because you will see that, so if I multiply all this thing and then try to, because I take this and multiply with the same thing, you can do yourself. You will find that there will be 4 terms. One is 0, another one is 0, and then one is 1, another one is 1. So 2. So your n
So 1 by
square becomes 1 by 2. So n becomes 1 over root 2. Okay, I'm not doing, you can do it yourself. So this is your Slater determinant for the ground state of helium atom. If I have the n number of electrons, so if I have a situation that we have n number of electrons, what will be the wave function? The wave function is going to depend on how many coordinates, 1, 2, 3, up to n. And you will see that normalization constant is going to be 1 by root over n factorial. And what are the terms? First one is going to be phi 1 1 alpha 1. This is fine. 1 means 1s or something like that. What is the next term? If I go along the row, what is going to happen? Electron number is not going to change, isn't it? What is going to change?
The spin state only.
Yeah, spin state is going to change. So what should I write here? What should I write? Because I'm talking about the ground state, not the ground state, but an electron system. What should I write? What would be this one? This is phi 1.
Alpha 2.
Yeah, phi 1 1. No, not alpha 2. It will be beta 1 because it's the same orbital, no? Like go like this. Then I have say m orbital. So this is phi m 1 and beta 1. This is fine with all of you. If I go down the row, what is going to happen? What is going to change? So this, so along the columns, this is like electron 1. So if I go down, what is going to happen? Your spin state will not change, but your electron number will change, isn't it? What is this going to be? Phi 1 to
2 alpha 2.
alpha 2. And what will be the last term? I can phi, tell me
1 n alpha n.
1, but for the nth electron alpha n. Okay, this is fine. So similarly I can go diagonally. What will be the this term? Can you tell me? You can go from here to here. This is going to be, if I go along this, it has to be function of 2, isn't it? This is going to be what? Phi 1 2. What is this? Tell me.
Beta 2.
Beta 2. Similarly, here what will be the last term? Phi m for the nth electron, and this is fine. What is m then? M is n by 2 for n even. For odd, it is this is the Slater determinant. Okay, again I'm writing it here. Can anyone tell me what is the Slater determinant for lithium? How many electrons are there? How many electrons for lithium?
3 electrons.
So 3.
Yeah,
So
so
it will
third
be 3 by
electron,
3.
third electron could be alpha or beta. I can take this to be beta. 3. So what will be the wave functions? I say 1, 2, and 3. It is going to be can anyone tell me? Phi 1s 1, alpha 1. No? Next, phi. Tell me. 1s 1, beta 1. This one? Phi. What will be this?
1s2.
No, it is
2s.
because your electron number will change, not change along the row, isn't it? This I consider this to be alpha. This is fine. What about the next? This guy, tell me. If I go down the column, what is going to change? Electron number is going to change, isn't it? 1s2. What is going to happen? Alpha 2. Then the third one is what about this guy? Tell me. Try to do yourself. What is this going to be? This one.
Phi 1s2 beta 2.
Yes. So let us do it. Again, this is for the second electron, isn't it? This is phi 1s2 beta 2. This one is going to be phi 2s 2 alpha 2. What about this one again? Phi. Tell me. You should be able to tell me now.
1 is 3 beta 3.
1 is 3 beta 3. What about the last term? Phi 2s. Tell me.
2s3 alpha.
This is for lithium. Now we try to put the third electron in 1s. I want to have something like 1s3. Do you have such configuration? with alpha spin? Do you have such configuration? Is it
No, sir.
possible? You
No,
know
sir.
from your experience.
Determinant,
No?
determinant will be 0.
And how can you show that this will be 0? So let me use a different color. If we try to do this, what is going to happen? Your phi 2s will become now phi 1s all throughout, isn't it? Huh? And then what is going to happen? The first and the third column will be
Similar.
identical. What will happen to the determinant?
0.
0.
And this is a name to this. So this state does not exist. What is this called? This is called Pauli exclusion principle, isn't it? Two electrons cannot have all the quantum numbers same. Or in other words, in one orbital, I cannot have two electrons with same spin state. Both are up, both are down. Here we have tried to put 3, isn't it? This is fine. This you know from your class 12 chemistry, isn't it? Pauli exclusion principle, you can show explicitly mathematically using Slater determinant. Is this clear? So if I have a determinant, if 2 columns or 2 rows are identical of a determinant, what happens to the determinant? What happens?
Becomes 0.
It becomes 0. Yes. So we have used that property of determinant. So up to this is fine. Then what about the fast excited state of helium? Let us do it. What is the configuration? And can anyone tell me what will be the wave function for this state? Any suggestion how to start, how to proceed?
So I guess it
Sir,
should be
configuration will be 1 is
1s1.
1.
Yeah, it is not going to be easy, I can tell you. That I can tell you. It's not going to be easy. Yeah, someone else is saying something or saying something. Any
So
suggestion?
the configuration should be 1s1, I guess.
What 1 is 1? 1 is 2, 2 is 1. Sorry, yeah, 1 is 1, 2 is 1. Yeah, sorry. You're right. But what will be the wave function? Wave function, tell me. This is a typo, but what is the wave function? 1 is 1, 2 is 1. What is the wave function?
We can start with phi 1s1, phi 2s2 into the spin.
Yeah, I'll tell you. I'll give you a trick, and this is quite useful. This is what it is. Okay. So the trick is as follows. So let me have a different color. This is 1s. This is 2s. One possibility is this, because being chemist, we like this. This is one possibility. And we like all the time we like pictures. What is the other possibility? See, everybody carefully, please listen to this part, because this is some trick I'm going to teach you. It is not easy otherwise. What will be the fourth one? Tell me. Down, up. Is this fine? Is this fine? I can.
Yes, sir. Yes.
Given 2 orbital, 2 electrons. Up, down, 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 up. Okay? Very easy. Is it easy? Okay, this is called, I'm calling it. So this is whatever. So this is, I'm calling it 1. Configuration 1, configuration 2, configuration 3, configuration 4. For 1, what will be the wave function? Say I am calling it psi 1, 1, 2. 1 means I don't look at other configuration. I have this. Only I have this, okay? So I'll have a factor of 1 over root 2. It will be there. And what will be the way, what is that called? Slater determinant for this? Don't look at this 3. Look at only 1. Now somebody has to tell me what is this. Phi, look at it. Phi 1 is?
Alpha
1.
Alpha 1.
Alpha 1. But then you have?
Psi 2s.
Yes. Which will be here, isn't it? Because this is for the second electron. 2s2 what? Beta 2? Is this clear? Because this is phi 1s1, the 1s1 has alpha 1, 2s1 has beta spin. This is fine? Diagonal elements. Is it fine? Tell me. This is up, this is down, up, down. And now I will use the rule of Slater determinant. The first row is for electron 1. This is for electron 2. Tell me what should I write? It is for electron 1. Can anyone suggest me what should I write?
Sir, phi 2s1, beta 1.
Yeah, because 2s, the orbital is 2s, 1, and this one is beta 1. What about this guy? Tell me. This has to be
Sir,
for
phi 1
electron
is
2.
Phi 1 is 2, alpha 2.
1 is 2. What is this? This is alpha or beta? This is alpha 2, isn't it?
Yeah.
This is the Slater determinant for configuration 1. Is it clear to all of you? This is very important that you get it. It's not very difficult, but it has a small trick. You have to put the diagonal element first and then use the rule of Slater determinant to fill up the other elements. Is this clear? If it is clear, then you should be able to tell me what is the Slater determinant for 2, configuration 2, which I am calling psi 2. Tell me.
Phi 1s1, alpha 1.
So in this case, it is going to be phi 1s1 alpha 1. This is fine. But what about the second electron? This is in 2s, but again alpha. So the diagonal element will be phi 2s for the second electron, but alpha. And then I fill it up. This is for electron 1. What will be the element here? Tell me. Phi
2s1 beta 1.
2s1. No, is it beta? Beta? Alpha or beta?
Alpha.
Tell me. Alpha, yes. Because alpha 1. What about this guy? This one? Phi? Tell me. 1s
2 alpha 2.
2 alpha 2. Similarly for configuration 3. What will be the answer? Can anyone tell me? Tell me. This is 3. 3 is phi 1s 1, but it is down, no? Beta 1. This is phi 2s 2
beta 2.
beta 2. And what is this? This is again for electron 1. This is phi 2s 1, but electron is
Beta.
up or down?
Beta 1.
Yeah, yes. Here it is phi 1s, no? It is 1s, isn't?
Yes.
2. What will be this will be beta or alpha?
Beta.
Similarly for configuration 4. So this is called, I'm calling 3. What will be the answer? What will be the answer? Tell me.
1s1 beta 1 and 2s2 alpha.
Phi 1s1,
Beta 1.
because this is down, but phi 2s2 alpha 2, sorry. This one is phi 2s 1. What is that? Alpha or beta?
Alpha.
Alpha.
What about this guy? 5. 1 is 2. What will be
Beta
alpha or beta?
Beta.
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 So you have all the Slater determinant for all the configurations. Is this clear? Now recall little bit of your class 11-12 chemistry. You remember that if I have a configuration, what is this called? Usually, what is this called? You have this or this. These are called triplet, isn't it? You know from your inorganic chemistry.
2s plus 1 is equal to 3.
Yes, a very hand-wavy thing. In this course also, it is going to be a little bit of hand-wavy because I could not teach you what is known as the addition of angular momentum. That I did not teach. But I'll give you a trick. So you have to remember these and these are triplet. Now triplet means there should be 3 states. What is the third state? They have the same energy and the 3 in number. What is the third one? Can anyone tell me?
Alpha beta plus beta alpha.
Yes, actually you have to remember the other one is this. This is also triplet, isn't it? So these are triplet. You have to remember this. What about the singlet? This is called singlet in inorganic chemistry. This one or this one. They're called singlet. But I told you that they're indistinguishable. So you cannot take only this one or this one. Actually, I am not doing it, but one can show explicitly quantum mechanically that this is not the triplet, but this is, sorry, the singlet. This is singlet. Okay. So up, down, minus down, up is singlet. Anish, you knew this, I hope. What about others? Then up, down, minus down, up is singlet. What about others? Singlet means what? What is the total spin angular momentum? S is for triplet. What is the value of S? Can anyone tell me?
1.
This is not the operator. It's the total spin. Here it is 0.
For singlet is 0.
And what is the ms value? Or total ms is here. This fine. Now, can anyone tell me which one is ms minus 1 in this configuration? Which one is ms minus 1?
The down.
Yeah, this guy is ms minus 1. What about this guy?
This is a plus 1.
And what about this guy? This side 0, isn't it? So here also this one has ms0, but it also has s0. That's why it's singlet. So now I can I write a psi singlet? What will be the psi singlet? Can anyone tell me? Looking at this scheme, so it has to be up down minus down up. So which one is up down?
1.
Psi 4, no? Sorry,
Psi 1.
1 and 4. So basically it has to be psi 1, 1, 2 minus psi 4, 1, 2. And if you do explicitly, you will see that it will also get another factor of 1 over root 2. You can check yourself. What about psi triplet? Psi triplet, there will be 3 wave function, no? What is the wave function for up in this case?
2.
2 is up, no? This configuration. So it has to be psi 2. What about I have 2 more, no? What is the next one? Also down, no? Down is which one? Psi 3. And what about this guy? Up, up, down, plus down, up, which is again psi1 plus psi4. It will also pick another factor of 1 over root 2. You can check yourself because of normalization. They have a linear combination, that's why. Is it clear? More or less clear? You have to go and practice. So then next I go to the next slide and I write down in a fashion which you can remember. So I have already told you how to write in terms of Slater determinant. So the excited state of helium is such that it cannot be written using only one Slater determinant. It has to be sometimes linear combination depending on the state of the Slater determinant. Is this clear? Is this clear? See, this is singlet is psi1 minus psi4 into some factor. Triplet is either psi2 or psi3 or psi1 plus psi4 into some factor. So another way of doing this is as follows, that psi singlet, let me do the singlet first, for which S is 0, MS is 0. Psi singlet is given by this 1 by root 2. I take the plus combination of orbital part of the wave function. So phi s1, phi 2s2 plus phi 1s2, phi 2s1. If I take the plus combination of the orbital part of the wave function, then what will be the spin part? Can anyone tell me? Can anyone tell me what will be the spin part? The space part is plus combination. What will be the spin part?
Minus combination.
It has to be antisymmetric because the total wave function has to be antisymmetric, isn't it? The spin part has to be antisymmetric. It will be 1 over root 2 into alpha 1 beta 2. Then what is the next term? Minus beta 1 alpha 2. So now you understand why these two 1 over root 2 comes twice in here. Okay, that's why it comes twice. That will be a factor of half. This is called for the singlet. Now can anyone tell me what will be the triplet? What is the value of S for triplet? What is the value of S?
There is 1.
S is 1. What is the value of MS?
Minus 1, 0, plus 1.
Very good. S is 1. MS 3 possibilities. Okay. So let me write down for MS minus 1. What will be the triplet state? MS minus 1. I have done it. So let me do it. So for the triplet, the space part is antisymmetric. Then what will be the spin part?
Only
Tell me.
beta 1, beta 2.
So if I do minus MS, then it will be beta 1, beta 2, isn't it?
Yes, sir.
This is for MS minus 1. What will be the MS plus 0? I'll write it later. What will be the for MS 1? This will be
Alpha 1, alpha 2.
alpha 2. Because here the spin part is symmetric. Space part is antisymmetric. And what will be the MS 0? You know this.
Alpha 1, beta 2 plus beta 1 alpha.
Yeah, your factor like this. And all these things, how to write using Slater determinant, I have done earlier. I could have done this at the very beginning. I could have gone the other way, but I did the other way. Okay, so let me repeat. Let me repeat. Let me repeat, for the singlet, the space part is symmetric and the spin part is antisymmetric. For the triplet, the other way, this is symmetric. For the singlet, this is antisymmetric. The total is antisymmetric, has to be, no? For the triplet, this is antisymmetric and the spin part is symmetric. But the total is antisymmetric. It has to be because of Pauli principle. The total. If I multiply this with this, it is antisymmetric. Okay. So this actually completes the discussion on spin in this course. So in the next class, we'll start something known as perturbation theory. And I'll give you some assignments. I'll give you some time. Maybe after a week, we'll discuss the spin and the angular momentum part while discussing the assignments. Is this clear to all of you? Any questions so far?
So for the lithium case,
Yes.
the electron which is in 2s, so it could
could
be
be
in
beta.
alpha,
Could be
it could be
beta.
in beta also. So
Yeah,
I
yeah,
have to
yeah.
take the linear combination, I guess.
The usual way you to keep can take alpha, but in general you can take a linear combination of these two determinants, that because both are equally possible.
Yes.
It's possible, but you can take only alpha or beta. That should be fine. Okay.
Okay.
I understand whether it is down or up. You're saying the third one. Any questions so far? Because I don't see much response. This is the problem. You should be asking questions. Any question? I have few minutes. We'll have discussion maybe after a week. After a week or half, we have a discussion session. Any question so far? Any question you can ask in the WhatsApp chat. You can discuss among yourself. You can email me. Better to use WhatsApp. Or if you are not comfortable, you can email me. Anything is fine. And no question is stupid question. Okay, you can ask any question. Don't ask question like how many marks will be there in say final exam. All these things you don't ask, but ask question on what I taught today or maybe day before. So I have discussed angular momentum and orbital angular momentum, operators, then spin operators, spin states, multi-electron system spin, Slater determinant, and while doing so, we also discussed this ladder operators for harmonic oscillator as well as for the hydrogen atom problem, and then for the spin. So this part, whatever I taught today, the first portion is from the book by, I showed you the book. This is the book by David J. Griffiths. And the other part which I taught today, partly from this book. Can you read this book? This is a physical chemistry book by Engel and Reid. Okay? Engel and Reid, physical chemistry. Any question? Anyone, BS, MSc, PhD, anyone can ask question. So no one has a question. So it basically means either nobody has understood or maybe you have understood everything. No question. If no question, then I'll just conclude today's session. So no question? Okay, good. Anish, you have no question? Ayan?
No, sir. Let us read again it from the
Yeah,
books and
go
also
and
from the.
read from the book and class notes,
Yes, sir.
videos, all these things.
Yes,
Practice
sir.
Slater Determinant a little. Everything you have to practice, all the operators.
Yes,
Little bit
sir.
of practice is important. Huh? Once you read yourself, it will be clearer.
Yes, sir. Let us read, and then if something strikes in mind, then we'll
Yes,
let you know.
write back to me on on WhatsApp or email me, whatever.
Yes, sir.
Okay,
Sure, sir.
okay, I'm stop presenting and now I stop recording. So the next